Today, we will look at the violin from the perspective of physics. A violin does not make sound by magic. Its sound begins when the bow rubs against the string. That vibration is transferred to the bridge, then into the body of the instrument, and finally into the air, which carries the sound to our ears. In other words, playing the violin means controlling vibration. First, pitch is determined by frequency. Frequency means how many times something vibrates in 1 second. A faster vibration produces a higher pitch, and a slower vibration produces a lower pitch. For example, the open A string is usually tuned to about 440 to 442 Hz. 1 octave above that is about 880 Hz. Next, the pitch of a string depends on 3 main factors: string length, tension, and mass. When the left hand stops the string, it shortens the vibrating length, and the pitch goes up. More tension also raises the pitch, while a heavier string lowers it. That is why the G string sounds lower and the E string sounds higher. At the center of violin sound is friction. The bow hair catches the string, pulls it, then the string slips, and then it catches again. This repeating stick-slip motion creates the vibration. Rosin helps make that friction stable. If the bow pressure is too strong, the sound gets crushed. If it is too weak, the sound becomes thin or scratchy. Another important idea is the balance of bow pressure, bow speed, and contact point. These 3 work together. Playing near the bridge can produce a more focused and brilliant sound. Playing near the fingerboard gives a softer and gentler tone. Good tone comes from balancing all 3 conditions at the same time. The strings alone do not make a large sound. The bridge carries the vibration into the body. Then the top plate, back plate, sound post, bass bar, and the air inside the instrument all take part in resonance. That is how a small instrument can produce a rich and projecting sound. Timbre, or tone color, is also shaped by overtones. Even when the pitch stays the same, the balance of overtones can change the sound completely. More high overtones create a brighter and clearer tone. Fewer high overtones create a softer and warmer tone. Vibrato is another physical process. The finger moves slightly back and forth, changing the vibrating string length and therefore the frequency. But good vibrato is not just random movement. It must keep a clear center pitch while controlling width and speed. Finally, resonance matters greatly. When intonation is accurate, open strings and the body of the violin respond more easily. That is why good intonation often feels more resonant and alive. So listening for resonance means listening to the instrument's physical response. In short, physics helps us understand how the violin really works. And when we understand that, we can produce sound more clearly, more consistently, and more musically.